is the right or the wrong value for algebraic complexity? Because you may not
I would not call this algebraic complexity in the traditional sense.
operators.
Yeah, but like property testing for continuously. So yeah.
Yeah. So we are very happy to have Vipul Arora from NUS. Vipul is Aruna Bhattacharya's student and he is visiting us for one day. He works in complexity theory and a lot of other fields. This talk is about property testing, specifically logarithmic testing over the reals.
Thank you. Thank you for taking the time out to attend my talk. This is based on joint work with my Bhattacharya, who is moving from University shortly. Noah Fleming is a faculty member at Memorial University. S. Tickelman, who is a postdoc at Boston U and MIT, and Yuichi Yoshida, who is a faculty member at NIH. So, let's hide this.
What's the news movement does not have?
No. I think from his.
So let's start with the motivating problem. You're given a function f from, let's say, f into f. F split f is some function domain, and you're given the function f y over laterals. You send x to the lateral, you get f of x back. And the property p over here is some non-trivial subset of this space of functions. And you want to test whether this function f is a number of the property p or not. And the complexity measure that you want to optimize is the number of queries you need to send to the oracle. And there are adversarial examples where just to decide this question, you may need to spend a lot of queries. So just an example is f a constant function. The adversary may just tweak f on one point, and to detect that one point, you need f on all values in the domain. This is a bit too much for our liking. So the question is, to reduce this query complexity, can randomization help? The answer is yes. But to do that, we need to relax the correctness requirements on our. And this is where the field of property testing comes in. So again, a property is some non-trivial subset of mathematical structures. You can have functions, graphs, distributions, whatever you are interested in. The property you have in your mind, the element A that you want to test is given to you, and you have a distance parameter, a distance function delta, and a distance parameter epsilon. And for any such element A, you want to accept A with high enough probability if A is a number of P, and reject A again with high enough probability if the distance of A from P is at least epsilon. So the notion of distance is dependent on the domain. We'll see what appropriate notions of distances are.
Is it possible to have a version of this where the rejection probability depends on epsilon? So I want it to be half plus some function of epsilon. Would that make sense?
That should make sense, but so instead of getting 2 by 3, you can have a 1 minus delta, and then you'll have a dependence of log 1 by delta.
Not 1 minus delta. So the justification is if epsilon is very small, then it's impossible to make a lot of queries.
Yes.
But I want it to be even for small epsilon, I want the guarantee to be half plus some function of epsilon.
That I think is not possible. Like, if you shrink this angular region where the algorithm is allowed to fail, you are asking a bit too much from the algorithm.
But I think in many situations you can make the rejection probability essentially equal to this epsilon. I mean, like for example, the BLR test, etc.
Yeah.
If the further you are from the property you care about, the more your test will reject.
Okay.
There's some trade-off, but usually there's some connection between what the 2/3 is and this. But I don't think you can get a half plus epsilon.
Okay.
Yeah.
Okay. So notice that in this setup, we were allowing two-sided error, but depending on our applications, we will require either soundness or completeness, which is basically asking for a tester with one-sided error. And this is what we end up achieving. So this whole field was initiated by the seminal work of Luby and Rubinfeld in the 90s. where they gave the first test of polynomial. So this whole work, or this whole field of work, was initiated by the seminal work of Blum, and Rubinfeld, where they gave testers for linearity of finite groups. And we'll see that our work is also heavily inspired by the VLR test. So before we go over loadability testing over continuous domains, let us see the earlier work which was on loadability testing over finite domains. So the property P is again the set of all polynomials over F, total degree D. You are given query access to F, and you want to test if F is in P or the distance of F from P is at least epsilon. The distance notion is the usual L1 distance with respect to the distribution being the uniform distribution over F. So delta of Fp is defined as you take the closest member G in the property P. You take the minimum fraction of the number of points in the domain over which F needs to be modified to make it equal to G. So yeah.
So F is the same as the capital A in the previous slide? Or
yes. So A is the number that you are testing for. And here we've specialized to the property being over functions from F and to F, or polynomials over F and to F, and the member is some function from F to F. So this field has been extensively studied in the works of Rubinfeld and Sudan, who gave the first loadability testing algorithm, followed by Safra, and more recently in the works of Bagale, Dinur, and Navon. And this problem also has crucial connections to more deeper computational ideas, namely probabilistically checkable proofs. Yeah. Not only over finite domains has it been studied, but also over finite subsets of infinite domains. Finite subsets of Q to the N. This problem has been solved in the works of Lipton, Rubinfeld, Sudan, and Kiwi, Magnus, and Santha. So this work of Kiwi, Magnus, and Santha is an excellent survey for studying loadability testing over finite domains. So now the problem that we are interested in, this question was, can F now be extended to continuous domains? Let's start with reals. And what are the hurdles we face on the way?
Why continuous? So the first step I would say is just Q to the N, right? Because that's only countably infinite.
Right.
So far you don't even have infinite.
Yeah. So we do study such sets as well. Lattice is 1 by BZ to the N. But our collaborators, Yuichi and Noah, they had solved linearity testing over reals first. So we were inspired to take up loadability testing over reals. So the first problem in this extension over reals is you need to define the distance notion appropriately. The distance notion in the finite domains was uniform, the L1 distance with respect to uniform distributions over Fn. But you don't have any uniform distributions over Rn. So you define the distance notion with respect to the distribution that you want to test. So you take an unknown, but a fixed sampleable distribution being supported over Rn. You define the distance of F from the property P with respect to the distribution as you take the closest member G in the property P, and you take the minimum fraction of the mass of the distribution D on which F needs to be changed so that it becomes equal to G. So spiritually, it's the same as the earlier notion of distance. Just instead of uniform distribution, you have a weighted distribution. And because we are taking an unknown distribution, we end up getting a distribution-free tester. We do not assume any knowledge about the distribution to start with. So the next hurdle is...
But you assume we can take samples from data.
Yes, without sample access.
Yeah.
So unlike the finite domains case, you are not even guaranteed that the function will have a polynomial representation. Over finite domains, while Lagrangian interpolation, you have a large enough degree polynomial representation, but over here, no such luck. So how this was a hurdle. And then the question, the idea of learning the polynomial and verifying, this requires n plus d choose d many queries, because if you do multivariate polynomial interpolation, in a degree d, in a total degree d n varied polynomial, these many monomials can be hiding. So just to do the polynomial interpolation, you would need these many queries. And this is a bit too much again for analytic. So we overcome all these hurdles and we solve this problem in already to the 5 plus d square by epsilon log 1 by epsilon queries. So notice that in the query complexity, n does not appear. So n can be taken as going to infinity, and the degree being much smaller than n is a low parameter over here. So therefore the low degree testing.
So here, should I just assume that basically real arithmetic is for free? I mean,
Yes.
Okay.
So we start with the case where you have real RAM machine available to you,
Okay.
and we sequentially remove those assumptions. Yeah. And as I said, our co-authors Noah and Yuichi had solved the problem of testing linearity in the exact arithmetic model over RAM. Yeah. Let's quickly see what our results are. So in the exact testing domain, you have the degree parameter D, you have f from R into R, you assume it's continuous, but this assumption of continuity then can further be relaxed to just have it be bounded on a large enough ball. So then you have distance parameter epsilon greater than 0, query access to f, and sample access to the unknown distribution D with respect to which you want to test. And we show that there exists a one-sided error, distribution free, poly D and 1 by epsilon query tester that accepts f with probability 1 if f is a degree D polynomial, and rejects f with high enough probability if f is epsilon far from all degree D polynomials over the distribution. So yeah, as Ramprasad said, that there are some hypercomputing things going on over there, but we resolve all of those. So again, salient features are n is the asymptotic parameter, d much less than n is a low parameter, and we beat the trivial learning and verifying approach by a long shot. Our query complexity is poly d and 1 by epsilon, completely independent of n. And we are the first one to solve this problem over domains, both continuous and discrete, with infinite subject.
So just going back to Raghuvansh's question. So if you have this over reals and it is distribution free, suppose your distribution is now supported only on the rationals, does that immediately follow? I mean,
okay. I think it should follow. Okay. Yeah. We do not require any.
It's not like the support needs to be full or anything. Okay.
Maybe you said this, but what is the complexity for the Noah and Yuichi linear?
So, good question. You substitute d is equal to 1 over here. And
So 1 plus 1 over
log 1 by epsilon.
Is it like taking random points and checking something in the context combination?
So it's BLR, but with sufficient modifications. And I forgot to mention in a recent source of submission, we are able to shave off the log 1 by epsilon factor as well. So with respect to the epsilon parameter, we are optimal. So the trivial omega 1 by epsilon log for testing this problem.
So the only queries you will be making are like you don't get to choose the point at all.
We do. So you have sample access to the distribution, and you can ask correlated queries to those.
Okay.
Yeah.
Okay.
Because the idea is to do testing on line restrictions.
No, in the sense that I'm just like, for example, suppose I ask. So typically in a BLR thing, you would be like, you query 3 points on a line, and then you will check if some correlation.
Yes.
So I can always sample 2 points at random. So that will give me 2 crazy points. The third point I need to choose, which is something on this line. So I need the distribution to have non-trivial support there, right?
Yeah.
So maybe the rational,
but we are able to make this work on integer lattices, rational lattices, in fact. So
what is the issue? No, in the sense that the previous question was about whether if the distribution was supported only on some subset, then do all your queries only come from this subset?
Yes.
But the problem is you're not just querying. There may be one correlated query that you're also making.
Yeah.
But I was like, what if that correlated query is not in your support?
So in that, we have an additional restriction that if you want to test with respect to say rationals, You want the distribution to be supported not only on the rational lattice, but also on the refinement of that lattice.
Oh, okay.
So,
Okay.
yeah,
Okay.
a suitable refinement, but yeah. Yeah. So, quick word about the machine model. For working with reals, we assume that you have
One more question. Maybe I'm going to fire it, but suppose I want to lift the degree up. Is there a way to view, let's say, a quadratic or a bilinear form as a linear form in a higher space, and then use the NOVA and UG result? Like I can just increase the variables to n square or something.
Then the coefficients of, like, you take one variable as a formal variable, the other one as coefficient from that ring, or
I was just thinking you have n square variables where variable I it's like variable I comma j is xi etc. Something like that.
Okay.
Because the queries do not depend on n, right? So I can change the
Right. I'm not sure about that, whether this can be extended that way.
okay.
Maybe we can discuss this.
Yeah. But you really mean no dependence, not even log n, nothing.
No, not even.
Log n.
No,
Okay.
not dependence on it. Yeah.
Okay.
So we begin by assuming you have a real RAM machine. Basically, your memory cells can store real numbers. Your memory IO operations with reals can be doable in constant time. Oracle IO operations with reals can also be done in constant time. Infinite bit precision arithmetic operations, basically addition, multiplication, and equality checks with reals, they are doable in constant time. And
All-time problem constant time.
yeah, no modularity is going on over here, so only addition, multiplication, and equality check. Yeah. So
You can encode within one round.
finally, on top of this, we require sampling from Gaussian distributions over Rn in constant. Yeah. To make our algorithm work over real world machines, we extend this result twofold. In the first setup, the query oracle to F can only output an answer with some finite precision. So in this case, we design an approximate logarithmic tester. So because the query oracle can only output with a finite precision, only finite bit precision arithmetic is needed in this case. So, and in the second case, where the oracle can only be queried on points describable by finite bit precision, which are basically points in a lattice, we design a discrete logarithmic tester. And for this, we show that instead of sampling from continuous distributions, the sampling from discrete Gaussian distribution in constant time is such. For only the approximate testing this, we have the parameter D, distance parameter epsilon between 0 and 1, F from R into R is continuous. D is a suitably concentrated distribution now. So what do I mean by suitably concentration? A suitable concentration is that you have a large enough radius ball in which at least 1 minus epsilon fraction of the mass of the distribution D is contained.
Okay.
So if your distribution D is not suitably concentrated, it means that almost all of the mass is at infinity, and testing with respect to those distributions is not very
So tau is the radius, it's the concentration. What is?
No. So there's a parameter capital R for the concentration, but it does not appear over here.
Okay.
It appears in this exponential in n to the d. It's hiding over there, but I did not mention that.
Hiding very well. Yeah. I don't see it.
Yeah. So you have parameters, additional parameters mu greater than 0, and tau, which is a large enough multiple of mu. How large? It's exponentially will be, but we live with that. You have query access to the and sample access to the distribution D, and we show that there exists a one-sided error, poly D in 1 by epsilon query tester, which accepts F with probability 1 if it's now a pointwise mu close function to some degree D polynomial. and rejects f with probability at least 2/3 if now for every degree d polynomial h on at least an epsilon fractional mass of distribution d, f is at least too far from h.
No, I'm just reading.
Sure. So notice that over here I dropped the word distribution free because we are assuming that it's suitably concentrated. And this idea of pointwise new close, this is motivated from the setup because we are assuming that the oracle gives finite precision answers. So if the real function is something like this, your answers will be in a band. So yeah, if it's like precision, this is proving itself. And mu is determined by the L bits of precision over there.
Why do you say, you said something about dropping the distribution free thing?
Because we assume that D is suitably concentrated over there.
But you still have D in the theorem. Like probability P is sampled from D.
Yes. No, so distribution free says you can't have any assumption on the distribution.
Yeah.
And here we are assuming it's suitably concentrated. So,
okay. So you have an example. Okay, fine.
yeah.
Got it.
So
got it.
this result is not distribution free.
Got it.
Sorry, so the tester, the only thing the tester is going to use about D is that the tester knows what this ball is. I mean, like,
Yes. Yeah.
okay.
Yeah.
So it just knows what radius contains almost all the mass.
Yeah.
Okay. That's the only thing it's going to
Yes. So basically, outside the radius R ball, the tester does not do anything. The error is just folded into the error of the test.
Is it possible to maybe sample some number of points of the distribution, take the largest L infinity point and use that as your R?
But then how do you guarantee that whatever is the sampling set that has actually captured the large?
If you have enough samples, then to capture every set with some mass, right?
No, but in the max value of f, that might be hiding somewhere, right?
The max value of F.
So the function is bounded in a large enough ball.
Yes.
Uh,
You just want D to be concentrated.
right.
So I'm just saying, instead of knowing R, you take an arbitrary D. You just sample points from it to see what is the rough size of it. You sample some number of balls and the L infinity norm should give you the R.
Yeah.
Then you can apply this.
Yeah.
So this would be distribution free.
But it's an assumption, right? That the distribution is concentrated. I mean, you don't need to know the concentration, but you need to know that it is concentrated.
I mean, there may be a distribution which is not concentrated at all.
But still, if you sample, let's say 1 over epsilon points, right, won't you get 1 minus epsilon fraction of it? In the
I mean, if you're in the continuous domain, right, you'll only make a finite number of samples.
okay.
There's some large ball that you would have gone to. Whatever process you have, you may then be led to conclude that, okay, within this much radius, all my epsilon, almost all my mass is there.
Yeah.
But that just could be false because the distribution, there is no such. So it looks like you need some promise about what this D is. Is that what you're
Yeah,
saying?
so
Is there
has a very heavy tape, like really heavy tape. So it decays very slowly as it's going infinity.
Is there an example just so I can calculate it?
So let's say something like an exponential, or maybe like a polynomial. Yeah, maybe like a polynomial, like 1 over n square kind of a thing.
I mean, if your CDF, I think, if it looks like 1 by Z sort of a thing,
Yeah.
then
Yeah.
the tails are always unbounded.
Okay.
Like no matter what you cut, I mean, there's too much mass on there. I think that
should bounded by what?
No. In the meaning, what I meant is that you can't. I can't give a finite number. I'm not saying it right. Yeah, I guess it just depends on the trade-off between what radius you cut off at and what the error is going to be. I'm not saying it right, but
I get what you're trying to say. I just want to have an example. So I can.
I would think basically an exponential is probably the.
Exponential, you would definitely concentrate. It will drop down very fast.
No,
Sorry, the CDF being like 1 by Z.
The CDF is 1 by z, it's not bounded.
That's not bounded, okay.
Not maybe it's like a polynomial, like one over x square kind of a distribution.
1 over x square is also, it's 1 is 1 minus 1 over x, right? So it will not a large table.
Maybe we can take it offline. I mean, maybe
But an example that I can think of right now, it's so you have Chebyshev distributions. They have spikes at +1 and -1.
Yeah.
If you dilate this distribution enough,
Yeah.
all of the mass is going to go to +infinity and -infinity.
It will not go. It will be at a large point, but if you take samples, you will have those points in you. So you can take enough samples, and then that is your radius.
I'm sure the things like that, but I'm not able to think of it right now. But we can maybe take this off.
Yeah, we can take this offline.
Yeah.
We'll just try to be louder.
Yeah. Okay, so let's go over the result for the discrete testing case. So you have the degree parameter d, b greater than 0 is the finest parameter of the lattice L, which is 1 over b0 to the n. You have again the distance parameter epsilon greater than 0, query access to f from R into far, and sample access to again a concentrated distribution supported on the lattice element. And we show that there exists a one-sided error, poly d invalid epsilon query tester, that accepts f with probability 1 if it's a degree d polynomial, and rejects f with high enough probability if f is now epsilon far from all degree d polynomials with respect to the distribution d. And this tester, as I said, additionally requires query access to f, not only on L, but an order in D to the 2D refinement of L.
A refinement of L is a final line.
Yeah. So you take B prime to be ordered in D to the 2D times B.
Okay.
Let's quickly see how do we build this tester. We begin with the testing for univariate polynomials. Testing for a univariate polynomial, the idea is to go via its derivatives. But for a degree d polynomial, we have that its d plus first order derivative must be identically 0. But we are in a query access world, and derivatives are defined as limits. So these objects are not finitely computable in our. We only have query access to. So instead of using the derivative, we use a finite forward difference operator. So the first order finite forward difference of f on the point x with the offset h is nothing but f of x plus h minus f of x. And this finite forward difference operator is connected to our usual notion of derivatives. So the derivative of f at the point x is nothing but the ratio of the finite forward difference operator with that step length with the offset h, and you take the ratio of the offset h going to 0, the limit. And higher order finite forward differences are defined inductively. So if you take the mth order finite forward difference operator of f, it's this combinatorial form. So you have the n plus 1 many points over here of the form x plus h up till x plus nh. And the coefficients of these f of these evaluations of f are combinatorial coefficients n choose I with alternating signs. And for notation's sake, we say that n choose I with the alternating signs are defined as unfolds.
Wouldn't you have liked to take the h's to be different? I mean,
so we are able to show that uniform convergence is sufficient. So instead of taking, if you take h's, it just becomes a bit too much to manage. So you will have a limit of h1 going to 0, limit of h2 going to 0.
No, I don't mean in that sense. In the sense that because in the finite world, the AKKLR test or something.
Yeah.
So that what it does, it basically looks at this parallelogram, a random h-dimensional parallelepiped.
Okay.
And basically takes the signed sum of all the function values.
Right.
Like for linear, you would have taken 0, a, b, and a plus b.
Yeah.
Those are the 4 points you would have queried, and you would have got linear. And this is the generalization. So there, the randomness was usually in terms of what these a's and b's are.
Yeah.
That corresponds to, in some sense, what your
H is.
what your h is. So I would have thought when you're taking a higher order thing, you will use the randomness by choosing sampling H1, H2 differently.
Oh, okay.
Uh,
No, but we only take one H, but the randomness of that H is covered in the random choice of points P and Q on which the line restriction polynomial is set, and we test on that line restriction.
okay, I guess it will become clear once we see the.
So the characterization of degree D univariate polynomial that we use from Friction from it. You take f from this interval a comma b to r. It's a continuous function, but continuity can be relaxed to again the boundariness assumption. If you then have that for every point x in the interval a b, and for all sufficiently small offsets h greater than 0, such that these points x plus h capital x plus b plus 1 h, they are in the interval a comma b. For all these points, if the linear form of this kind, summation alpha f of x plus ih, if this is 0, then f is a degree D univariate polynomial on the interval a comma. And a brief historical note is that Cauchy had shown this characterization for linear functions, f of x plus y is equal to f of x plus f of y for all points x and y in the domain of f, assuming f is continuous. If you don't have continuity, then you have the function is additive, but not necessarily a linear function. And then Fraser proved this theorem, not extending this theorem from linear to degree D polynomials. And Szydzelski in 1959 extended this characterization to functions that are now bounded in some interval. So what we end up using is this characterization from Szydzelski. So this was the story over univariate domains. We are interested in multivariates. How do you go from multivariates to univariates? The tool that we end up using is of random line restrictions. So an arbitrary line in Rn can be expressed as a linear form A plus IB. A and B are vectors, and in Rn, I is a real number. For any point, for any vectors A and B, you call the univariate function f sub AB as a restriction of f on the line LAB. If f sub AB of x is equal to f of a plus xb, x is a formal variable. And it's easy to verify that if f is a degree D polynomial invariate, then f sub AB is a degree D univariate polynomial for all points AB. Because in every monomial in f sub AB, the x degree will be at most D. And using all this, the key idea is to test then if the P plus first order finite forward difference operator of f restricted to random lines, this is identically C. So you take Gaussian random points of this form and zero rate arrays for some select set of data, and you test whether the D plus first order finite forward difference of f sub PQ with the offset h is equal to 1. This is 0 or not. So yeah. And surprisingly, only a finite number of these tests are needed to verify whether this characterization this holds over a small open ball B0R with high probability. So you test for sufficiently many repetitions whether this is not equal to 0. The moment you find a witness, you discard the function. If you do not, then you have a guarantee that on a small enough open ball, the function is close to being a degree D polynomial.
Sorry, so the samples are according to essentially some some interpolated normal type thing. So it's not drawn according to the distribution D.
So there are two parts of the tester.
Okay.
The characterization test is with respect to the Gaussian distribution.
Okay.
This helps us to define a self-corrected version.
Oh.
Right? And the distribution free tester comes in the distance estimation subroutine between f and the self-corrected version.
Okay.
So
this is not the test. We are not just going to pick P and Q according to this normal distribution and just check the forward difference.
it is a part of the test.
Oh, it's a part of, but it's not all of it.
No, it's not all of it.
Yeah.
So if you do not find any witness in this test, then you can show that the self-corrected version G is a degree D polynomial. And then the distance estimation subroutine between f and G in a sufficiently many repetitions will certify that f is then indeed close to a degree D polynomial, which is G. So this distribution free setup was introduced by Halby and Kushilevitz, and we build upon that. Yeah. So pictorially, the characterization test is nothing but this. You take random points, Gaussian random points P and Q. And on this line, you take D plus too many points, P plus Q, P plus 2, P or P plus D plus 1, 2. And you test whether this linear form, this is 0. And notice that you are evaluating f on this line on D plus too many points. F of P plus IQ, I going from 0 to D plus 1. But if you restrict your attention to I going from 1 to D plus 1, you have D plus many unique points on a line. And to interpolate a degree D univariate polynomial, that is sufficient. So with these D plus many points, you get a self-correction idea on this line itself. You learn a degree D univariate polynomial on this line and assign the value of that univariate polynomial on the point P. Okay. I'll come to that in more detail. Yeah. And also the radial projection idea of Yuichi and Muha. This is crucial to make our analysis work over reals. Their idea was you take any point P in R and you project it radially into a small open ball B0R. And in the analysis spits up what the value of R is going to be. It's specifically it's 1 by D to the 6. And this then allows us to say that testing only at finitely many points is sufficient to guarantee that if you do not find a witness in these tests, then the function is going to be appropriately well behaved. Okay. And this is also used to define a self-correction notion G for it meaningfully. So let's see what this notion is. To define G to make sense of it, you assume that the characterization test you just saw, this fails with low enough probability. The probability of failure rho is at most 2/3. Then for every point P in the ball B0R, you define G of P as a majority of GQPs, where GQP is nothing but the degree D univariate polynomial you just interpolated on the line LPQ.
Majority.
Yeah.
But it's a real valued function.
Yes.
Right? So,
So the majority is well defined, assuming that the characterization test did not fail.
Oh, I see. Then you'll have one number to
Yes.
this. Okay, fine. Got it.
So the existence of the majority is guaranteed by the characterization test passing with high enough probability. And G is well defined as in the ball B0R. Then follows from collision probability analysis. You show that for random values of Q1 and Q2 according to N0I, GQ1P and GQ2P, they are the same with high enough probability. And this in turn sets the radius R to be 1 by D to the 6.
How do we set the radius to be 1 by?
So to ensure that this collision probability analysis, this collision probability is large, R is set to be small.
Okay. But it's not clear from the slide.
Yeah, but I'm pushing a lot of things under the hood. So yeah. And for points P not in the ball B0R, you define G of P via radial interpolation along the line L0P.
Okay. What does that mean? What do you mean by radial interpolation?
I'll understand.
Okay.
Yeah. So the idea of using radial interpolation is this. You take any point P, you connect it to the origin. You get a line L0P, you intersect it with the ball B0R. Since you are over reals, you have sufficiently many points in this intersection region. You take D plus many unique points and you interpolate a degree D univariate polynomial on this line. And then for every point P on this line, you extrapolate the degree D interpolate you just learned. So therefore, you get the value of GP defined appropriately. Okay.
So why is 0 outside B0R in your picture?
Good. No.
So why is 0?
So the 0 starts there.
No. So it's L.
There is a point L.
So this is
that is the line L0P.
I see.
Yeah.
Yeah.
So it's P is somewhere over here, and 0 is in the center of B0R.
Okay.
And the line is L0P.
Okay.
Yeah. Maybe I should have said L bracket 0, comma. Yeah. So let's quickly see a proof of correctness. In the yes case, f is a degree d n-variate polynomial. So f sub a is a degree d univariate polynomial for all points a, b, and n. So the characterization test trivially passes for all such choices of p and q. And therefore the tester has one-sided error. In the no case, when f is epsilon far from the property p, you want to show either the characterization test itself would reject f with high enough probability, with probability at least 2/3, which if it happens, we are very happy because we have rejected f, which is what we want. But if then that does not happen, the second part of the tester kicks in, the distance estimation subroutine, which we claim will reject f by checking it against its self-corrected version g. Now notice that if the characterization test rejected f with probability smaller than 2/3, the previous slides we had that g is a well-defined function. The self-corrected function is a well-defined function, and we show that it's in fact a degree d n-variate polynomial over Rn. And since by premise f is epsilon far from p, f is also epsilon far from g. So delta sub b of fg is at least epsilon, and then by sufficiently many repetitions, or the epsilon 1 by epsilon many repetitions, you would find a mismatch witness with high probability.
So at this point, you're just comparing f from g. So maybe something like Schwarz-Zippel would work now?
Schwarz-Zippel.
Here is an infinite domain thing.
Oh yeah. But then it's even easier, right? You can take random points.
Yes. So
Unless you're
I guess you need, you need a whatever, I don't know, a cube version of Schwarz-Zippel, I guess. I mean, you sort of want to say that, if the function was different, then at a random point, you're not just different, you are different by a sizable quantity. But so I just want to make sure that I understand this test correctly. So I'm going to sample a point P according to the distribution. That point P is somewhere in this big ball.
Yeah.
So let's draw the line from P to the origin. Now, in the small ball, I'm going to query a lot of, let's say, random Gaussian points.
Yeah.
Okay. And use that to figure out what should be the self-corrected value at P.
Yeah.
And I'll check against whatever is given in the origin.
Yes.
Okay.
Yeah.
I see. Okay.
And the probability that in all of these order 1 by epsilon interpretations, you do not find a mismatch awareness is going to be at most 1 minus epsilon to the order 1 by epsilon. So that is going to be here. Let's quickly see how do we go from the finite domains analysis to domains with infinite support. As I said, our work is inspired from the BLR test. Let's quickly see what the BLR test is. So it begins by sampling uniformly random points from f to the n. You sample p and q, and you reject if f of q plus f of p minus q is not equal to f of p. Over f to the n, f of p minus q is equal to f of p plus q. So yeah. And if f is linear, the test will always accept, because f of p minus q would be equal to f of p minus f of q. F of q's will cancel out, and the left hand side will always be equal to right hand side. The self-corrected version G over here is defined similarly. So you take the majority over G to P's, where Q is now uniformly distributed to uniformly sampled from to the n, and G to P is nothing but f of Q plus f of P minus Q. So you take these random points P and Q, you interpolate a degree 1 polynomial from these two many points, and you assign the value of that interpolant on the point P on this line, LPQ. And you can think of this GP as every Q has contributed an equal vote in deciding the value of GF at every point. The crucial thing over here for this analysis that we need is, if you notice that over f2 to the n, if point B is fixed, Q is sampled uniformly from f2 to the n, then the other point P minus Q is also sampled. The distribution of P minus Q is also uniform on f2 to the n. We want a similar behavior, but the problem is there are no uniform distributions over R to the n. The question is, do we really need uniformity? Turns out no. All we need is a translation invariance statement of this form. if you take any fixed point P in Rn, if the distribution of Q is according to some distribution D over Rn, you want to ensure that for all choices of I in 1 after B plus 1, these points P plus IQ, which were on this line LPQ, their distribution is similar to the distribution of Q. And this is where the Gaussian distribution comes to our aid. Because if Q is sampled according to N0I, then for all fixed points P in Rn, for all choices of J in P plus 1, P plus JQ is sampled according to the distributed according to NP J square. It's not exactly N0I, but we can deal with this much. So with this, the question is, how do I design a tester that works for all points P in Rn? This is where an information theoretic argument helps us. So the argument is, for all scaling scale n, the total variation distance between n peak n0 ki and n peak ki is at most the L2 norm of P times k by 2. Okay. So P over here was fixed. If I can ensure that the L2 norm of P is small, NP ki over here can be approximated by n0 ki in the design of the test.
See, and this is the radius now.
Yeah. So to ensure small p2, you really project the points p from R to small. So with all of this, the task that then remains is to prove that if the tester did not reject with high enough probability, then G is a degree D n-variate polynomial. So G was defined incrementally, first in the ball and then outside the ball. So this proof should also be incremental. So the first part is to prove that on every line restriction on all line segments in the ball B0R, G is a degree D univariate polynomial. And this follows from the characterization test not rejecting F with high enough probability, as well as the collision probability analysis. Then from the degree D univariate polynomials, you construct a degree D n-variate polynomial representation for G, not on B0R directly, but on a small hypercube H contained inside the ball B0R. And this is where Schwarzschild comes in. And finally, once you have a degree D n-variate representation for G inside the hypercube, you show that this representation agrees for points outside H as well. This is simply an extrapolation pattern, because G was defined in this fashion. Let's quickly see how do we construct a multivariate representation from univariates. So it's a vectorial argument over here. So the argument follows via induction on the degree, on the number of variables n. So you take this hypercube H, you take D plus 1 many slices of the hypercube H parallel. And by the inductive hypothesis, on all of these D plus 1 many slices, you have the function G to be a degree D times n minus 1 variate polynomial. So the first proof is not a degree D, but a degree D n variate polynomial representation. So we first construct a degree Dn times n variate polynomial representation. So therefore, by the inductive hypothesis on all of these D plus 1 many slices, H has a degree D times n minus 1 variate representation. These slices are all parallel. So you take a line L that is perpendicular to all of them. And on this line L, by the first part of the analysis, G sub L of Xn is a degree D univariate polynomial. So you have n minus 1 variables and a degree of D times n minus 1 over here. And you have an additional variable and a degree D for this line. You stitch them all together to get a degree Dn n variate polynomial representation. And in the next step, this degree is brought down from Dn to D via another radial argument. So at the conclusion of this step, in the pink region, you will have a degree D n variate polynomial representation for G. what can we say about G outside the pink region? Specifically, B0R minus H, the green region. So you take a radial line, it intersects with H non-trivially, and if you're over reals, there are sufficiently many points on the intersection in the green region as well as the pink region. So whatever degree D n variant representation was in the pink region, that would be carried over in the green region as well. So via this argument, over all points in B0R, you now have a degree D n variant representation for G. And the next step outside B0R is even more simpler, because outside B0R, G was defined by extrapolation. So whatever degree D n variant representation you have in the ball, it extends outside the ball as well. So this completes the argument that G is a degree D n variant polynomial over. Let me wrap up by saying a few quick words on the approximate and discrete tester. So in the approximate testing idea, you do not have the guarantee that G is a degree D n variant, G is a degree D univariate polynomial on all line restrictions in the ball B0R. So instead of what you have instead is G circles are only sufficiently close enough to degree D univariate polynomial representations. So from this sufficiently close enough, we are able to construct a pointwise mu close degree D n variate polynomial representation. So this is where tau being large enough comes in.
Wait, what is happening here? I'm totally
Yes. So in the earlier analysis, we had the G sub Ls. They were degree D univariate polynomials.
Precisely, yeah.
But over here, what we have is G sub Ls are only sufficiently close to degree D univariate polynomials.
Okay.
So that stretching together argument is not going to work.
Okay.
So instead, we are able to show that.
So this is an alternative to stitching?
You can say that, but we just show that there exists a polynomial, a degree D n variate polynomial that is close enough to H.
Okay.
So yeah.
Sorry, by close enough here, this means that in terms of its evaluations, so previously, if for example, if you're close enough in terms of the coefficients all being within a whatever, epsilon or something like that, you have about n to the d. Oh, but this is exponential in n to the d.
Yeah. So we here close enough is in pointwise close enough.
As in, you want this to happen at all evaluations within the small point.
Yeah.
Okay. So this is a double exponential in d.
Yes.
Okay.
Yeah.
Well, I would have thought it should be n to the order d, because you have n to the order d coefficients, and union bound will give you something like n to the order d.
But how do you bound the distance, distance from every coefficient?
Radius to the D. Because the points are close. I will also expect something.
Sorry, in the previous case, when we said suppose the test succeeds.
Yeah.
If the test succeeds, then it is telling you that the self-corrected version is basically close to F. Right? I mean, like if the test succeeds, that's what it means.
Yes.
We know that the self-corrected version, if the initial characterization test works, the self-corrected version is actually a low degree polynomial.
Yes. Yeah.
And therefore, together they should tell you that this is the F also is close to a low degree polynomial. So, like, okay, but this is I'm not being precise in this thing, but what is the subtlety I'm missing? I mean, like, so the self-corrected version is close in a different norm, is it?
Yeah.
Like, what is the...
So it's what we have is for all points x in H, G minus our hidden polynomial H hat. This is at most this. I think it's This is at most.
Oh, sorry. This is happening because you are going from the univariate to the multivariate.
Yeah.
Oh, and this is the loss that you end up getting as a result.
Yes.
Oh. So the self-correction is defined at a line level.
Yeah.
You want to go from there to a multivariate self-corrected version somehow.
Yeah.
And that seems to incur some.
Yeah.
Okay.
So because the test is also on a line level.
Yeah. Okay.
And this model allows us to handle inputs, noisy outputs by the Oracle, where you have, in the yes case, there exists a hidden polynomial h hat, so that for all points x in Rn, f minus h is at most an absolute value, at most half. And in the no case, you have the guarantee that for every polynomial h hat, on at least an epsilon fraction of the mass of the distribution D, f minus h hat is at least beta. So beta is a multiple of alpha over here. So we test f for the characterization approximately in this case. So instead of testing whether the linear form summation alpha f of x plus ih is 0, we test whether that is small. Okay, and you reject, you prove that if the Ross characterization test rejects f with low enough probability, then you can construct a degree D n-varied polynomial that is close enough to f. And one subtlety over here is that approximate tester assumes that distribution D is suitably concentrated. It's not diffused. And instead of using the mean, you use the median to define G, because median is more robust to noise. Finally, the discrete low degree tester, which is testing on integer or rational lattices. Instead of sampling from Gaussian distribution, you sample from discrete Gaussian distribution of this from GLS, because the test is with respect to lattice L. So GLS is nothing but N0i intersected with the lattice L and the probability being renormalized on these points. And the crucial piece of analysis over here was to show that on a fine enough lattice, if you take minutely translated discrete Gaussians, they can be approximated by the corresponding discrete Gaussians centered at the origin. So this was a part of the analysis earlier as well, where we were showing that the total variation distance between NPKi and N0Ki was small. So that allows us to design a tester for this case. The formal theorem is this, that the total variation distance between this form and this form is at most 4k theta. All of this. Open questions. The tightness question with respect to the query complexity is unresolved. Our upper bound is order d to the 5. The lower bound is only omega of max of 1 by epsilon comma d. So there's a open thing to close. And with respect to epsilon, as I said, we are able to close that gap. So instead of 1 by epsilon log 1 by epsilon, we now have 1 by epsilon query test.
So where did the d to the 5 come from?
In the
characterization
test. So to make all of the covariances of p plus iq handleable, we need to test over sufficiently many scalings. And our approximate reconstruction blow up of this factor of tau being exponential in N2 is rather large. Can this be scaled down? This is another question. For specifically for D is a good one, for testing additivity, we were able to bring this down to in fact only a polynomial in N. So if you substitute D is equal to 1 over here, you get tau is equal to exponential in N, but the final bound of polynomial in N was also shown. And finally, the discrete tester requires Oracle access to F not only on the lattice L, but also on a finer lattice L. Refinement of that. Can this requirement be removed? Finally, our paper is accessible over here. Thank you for that. Questions?
Any questions?
So you mentioned in the previous slides that for the removal uniformity, you needed some translation.
Yeah.
Write that so that you get the reason exactly.
So what we want is the distribution of P and P plus Q in the BLR, that was identical. So for our analysis to go through, we also want the distribution of the points P, P plus Q, P plus 2Q, up to P plus 1Q. These are similar.
Those points are involving in your forward reference.
Yeah. So to make the distribution of those points handleable, we needed that translation invariance kind of state. So just translating by P would have been fine enough, but P plus I cube, the distribution changes. Instead of N0I, it becomes N0I square.
So, if I'm not wrong, if I remember correctly, there are three type of difference operators on right? So,
Divided differences.
yes, so the third one, I think that takes two equal. Wouldn't that make it better than the forward difference? Yes, sir. If I'm remember correctly.
We've not explored that.
So there are three different difference operator: forward, backward, and another was that takes balance. Yeah, the balanced one. Because there are three difference because of the fact that those works differently in the same domain, in a discrete domain, to take the parameters very nicely. Like this.
Sorry, but backward difference, you're just going to look at x minus h minus
Yes,
f of
yes,
x,
yes,
and x plus h and x minus h.
yes.
But I don't think it will make a difference because of the randomness here. I mean, it's like, I mean, forward difference at x is the same as backward difference at x plus h or something.
Do you have something like this, right?
Yes, that was it.
So this is like backward difference with respect to h at x plus h by 2
No, that is
or something. I mean, I think all of this will be observed in the. I don't think distribution will make any difference.
okay.
More questions? Yes, it's time for the and this.